Thank you for your presentation. Good morning to everyone. And I'm Martina Tarsi from Università Politecnica delle Marche in Italy. Today I will present a research about the assessment of life safety in case of fire emergency during the design phase. Fire safety encompasses a set of measures and practices designed to prevent fires, protect people and property from the damaging effect of fire. In the Italian fire regulation, there are 10 measures to be observed for fire design. These concern passive, active, and management protection measures to be adopted to prevent the occurrence of fire. Of all the measures involved, this research focuses on life safety of occupants in terms of safe evacuation. Designers can either apply the compliant solution provided by the regulation or can adopt the performance-based approach, which requires to demonstrate their solution meets the fire safety objectives. Italian fire regulations also allow for the adoption of international standards. Likewise, American fire regulations allow both prescriptive and performance solutions. Designing in a BIM environment requires the contribution of several skills. This collaborative approach enhances the efficiency, accuracy, and overall quality of the design process by leveraging digital models and data. In particular, we focus on the performance-based design of fire safety in buildings. It requires verification of the achievement of initially set objectives over several design options. Designers must, from time to time, test their design options by using external tools. Our research suggests procedures to facilitate this integration between the design process in a BIM environment and the quantitative assessment of design options. Therefore, the aim of this research is to develop a framework compliant with a BIM environment, capable of implementing performance-based procedures to assess the degree to which fire safety objectives are being met in terms of occupant life safety through the use of a key performance indicator. Two main gaps resulted from the state-of-the-art analysis. The first one concerns an assessment of the safety of occupants at a macroscopic level, missing an explicit representation of the effects of fire on occupants. The second one concerns limited interoperability between BIM and fire prevention tools, being mainly unidirectional from BIM to external tools. For these reasons, we have investigated two research questions. The first one investigates what type of framework can support the life safety assessment in case of fire or of several design options. The second one concerns what KPI can be defined to display the results of simulation and assess design options. The performance-based approach is facilitated by the adoption of KPIs. The KPI to assess life safety was taken from the Italian fire regulation as the safety margin, which is the difference between ASET and RSET. ASET is the available safe egress time, and RSET is the required safe egress time. The minimum required threshold in Italian fire regulation is 30 seconds, which is the threshold set in the test case reported in this paper. In addition, our evaluation overcomes the current approach based on calculating ASET and RSET only at limited number of locations in a building. Rather, we aim to assess occupant safety throughout the building by discretizing the whole area using a grid. The KPI, in addition to assessing any design options, provides a clear and immediate representation of safety condition levels for occupants. In order to answer the research question formulated, we develop a framework to support the designer choices during the assessment of life safety in case of fire emergency. According to the performance-based approach, KPI must be identified as the first step. Once a BIM model of the building is available, in this case implemented with the authoring tool Revit, it is necessary to select the design fire scenarios. For the demonstration purposes of this research, the predefined design fire scenarios provided by the US fire regulation NFPA 101 were chosen. This regulation provides us with 8 starting design fire scenarios on which to develop the most appropriate scenarios based on the specific case. Required data for further evaluation was extracted from the BIM model with the help of the Revit Dynamo plugin. This step automatically provides input data for simulation tools. We have used two different software for simulation, the Fire Dynamic Simulator, FDS, for the fire simulation, and the ULIC Pedestrian Simulator for evacuation simulation. Both simulation tools allow space discretization by providing results for each individual cells. The simulation outputs, including available and required time for occupant evacuation, were then represented graphically. 3 Python scripts were implemented for this step to create the maps with the ASCT, RSCT, and safety margin times, our KPI. These maps were produced in order to suggest what areas in a building are critical and what countermeasures can be adopted to improve life safety in the event of a fire. Finally, these maps were imported into the BIM model, allowing your stakeholders to visualize the results clearly and immediately. Dynamo was used to import KPI values from Python into Revit. Each cell of the grid in the BIM model was assigned a KPI value, color green if the KPI was within the safe threshold, and red if it exceeded the threshold. The entire procedure should be applied to all design options assumed by the designer for each design fire scenario. The final map containing KPI is the difference between the shortest time computed by every fire simulation and the longest time needed by every user for evacuation at every cell of the discretized BIM model. Thus, designers can propose an alternative design option to enhance any unsafe location and retest it on the same fire scenario. If several candidate design options are valid, the designers can determine the one that represents the best trade-off. The feasibility of the proposed framework was assessed using a pilot building located on the campus of the Politecnica University of Marche in Ancona, which hosts the School of Medicine. For the purposes of this research, we consider only the ground floor of the building. 2 of the 8 predefined NFPA scenarios were selected on which to apply the methodology. Once data was extracted from the BIM model, simulation were started. In this slide is reported the first design option for the first fire scenario. We can see how the output of FDS is converted into the asset map, which represents the times available for evacuation in each set of cells. The RSCT map is created from the trajectories of the occupants and the corresponding times required for their evacuation. By subtracting the RSCT map from the ASCT map, we obtain the difference map. This map was subsequently imported into the BIM model. Examining the imported map in Revit, the designers immediately notices several red points, indicating areas where the KPI exceeds the threshold. At this point, the designers must formulate an alternative design option and retest it on the same fire scenario. On the overall, in this first fire scenario, where the fire earth was located along the main escape route, 5 design options were evaluated. In the first 4 design options, there is at least one location where KPI exceeds the threshold. The last option, where all points are safe for occupants, is labeled as the candidate design option. Likewise, the second design fire scenario was analyzed, with the fire earth located inside the room where the highest fire load was expected. In this case, there are 2 candidate design options out of the 3 that were analyzed. To sum up, the graphical visualization of the KPI in the form of maps enables designers to immediately pinpoint those locations in the building that are critical for the occupants. Furthermore, with the help of the visual approach, the designers can assess the assumed design options over several design fire scenarios in a quantitative way. The KPI initially chosen to monitor fire safety objectives was mapped inside the BIM environment, importing maps created through Python. For future research, a possible recommendation involves identifying additional key performance indicators related to other domain of fire safety engineering, such as structural safety, and the creation of decision-making models to select the best trade-off among the selected design options. Thank you.